Now today's bedtime lesson is a bit short, but today we're going to find out about halos and coronas tonight. Now, let's find out about halos and coronas and how they form. We're first going to look at halos. Halos require ice crystals to form, either from high cirrus cloud of free-falling crystals. Typically, sunlight or moonlight is reflected by ice crystals, producing a white halo. However, if the light rays strike the light at a particular angle, some light may be refracted. In such situations, the halo will have a faint coloration. The majority of ice crystals are hexagonal or six-sided, and the most common angle of refraction through such a crystal is about 22 degrees. This is the most frequent type of halo, and they are named 22-degree halos. Crystals with a different structure or that are at a different angle to the sun may result in halos that vary in size. Small halos produce at 9 degrees and larger ones at 46 degrees, and relatively common. And in some cases, only part of a halo forms, appearing like an arc. In the past, halos and other such atmospheric phenomena were used in an empirical form of weather forecasting before the development of meteorology. There is some degree of truth in this. The high cirrus cloud, which contains the ice crystals required for halos to form, often signifies as an approaching frontal system. However, in many cases, the front will be inactive or simply change courses from the area, producing no rain. Now that's part 1 out of halos and coronas. Now we're going to look at coronas now. It is common for most optical phenomena to arise through a combination of refraction, and diffraction, but coronas form from a different diffraction alone. Diffraction is the apparent bending of waves around small objects and spreading out of waves past small openings. Think of a wave bending around a cove at the beach, or waves spreading out as they pass through an opening in a harbour wall. In terms of the diffraction of light waves, an example is a corona. These are most common around the moon, where the diffraction of uniformly sized water droplets cause white light to separate into colour. The smaller the droplet, the larger the corona. Although they are visible around the sun, the corona produced is weaker than the bright direct sunlight itself, making it harder to see. The ideal conditions occur when the moon sits behind newly formed mid-level clouds, such as altostratus. Newly formed clouds have the same size droplets, but as the cloud develops, the droplets vary, causing irregular shaped rings and more diffuse colours in the corona. Now here's a surprise. We're going to do a part 2 in this video right away. In this part 2 In this 2 out of 1 video lesson, the second one we're going to look at is a beautiful optical and why we see them. They're called the Northern Lights, and we're going to find out how and why they are forming and where to see them. The Northern Lights, also known as Aurora Borealis, appears as large areas of colour including pale green, pink, shades of red, yellow, blue and violet in the direction due to north. During a weak aurora, the colours are very faint and spread out, whereas an intense aurora features greater numbers of and brighter colours which can be seen high in the sky with a distinct arc. Hold on a minute. The Northern Lights are best seen in darkness, away from any light pollution. The lights generally extend from 50 miles to as high as 400 miles above the Earth's surface. Now what causes them? The Northern Lights occur as a consequence of solar activity and results from collisions of charged particles in the solar wind colliding with molecules in the Earth's upper atmosphere. Solar winds are charged particles that stream away from the sun at speeds of around 1 million miles per hour. When the magnetic polarity of the solar wind, is opposite to the Earth's magnetic field, the two of them combine, allowing these energetic particles to flow into the Earth's magnetic and north-south poles. Auroras usually occur in a band called the annulus, a ring about 1,865 miles across. centered on the magnetic pole. The arrival of a coronal mass ejections, or CME, from the Sun can cause the annulus to expand, bringing the aurora to low latitudes. It is under these circumstances that the lights can be seen in the UK. Depending on which gas molecules are hit and where they are in the atmosphere, different amounts of energy are released as different wavelengths of light. Oxygen gives off green light, and when it hits 60 miles above the Earth, whilst at 200 miles rare, all red auroras are produced. Nitrogen causes the sky to glow blue, yet then, when higher in the atmosphere, the glow has a purple hue. Which weather conditions are best? The best conditions to view them are when the sky is dark and clear of any clouds. Cloud cover ultimately blocks the view of the light. Ideally, the lights will be best viewed away from any light pollution. In remote areas, facing the northern horizon, north-facing coast produce some of the best viewing locations. The northern lights are most active during the equinox and solstice in March and April and September and October. And where can you see them? Predominantly, the northern lights are best witnessed in Scotland, North England, North Wales, and Northern Ireland. However, under severe space weather conditions, the lights can be seen throughout the UK. That's all for today, but I have one more thing to tell you. We have our final Minecraft videos coming up just before I say goodbye for a few months. Hopefully, fingers crossed, I'll have them uploaded. If not, I'm a meanie, so see you for the next Minecraft one. Part 1 will be coming out soon. Bye! And this build is called Travelodge. Bye!